Hello everyone and welcome to Fisimania. I know it's been a long time, but we're back with a lot of content and hopefully we're going to be learning a little bit more. And in this case, I'm going to be starting a new series, which is going to be about my specialization for my PhD here at the University of Florida, which is in the field of cosmology. And to do so, I'm gonna do it with 3 books and the help of some online YouTube series as well in cosmology by Leonard Susskind from Stanford. But the main content is going to be coming from this book, which is a course in cosmology by Dragan Horerer at the University of Michigan. Then we're also going to be the other 2 books that we're going to be using. One of them is going to be Cosmology by Daniel Baumann, and then another one which I don't have with me right now, but is Modern Cosmology by Scott Dodelson. So without further ado, let's go ahead and start and let's learn some cosmology. All right, so for this first class today, the content that we're going to be looking at, okay, so content, we're going to start by basically taking a look at the goals of cosmology. Then we're going to be looking at some important facts that happened, let's call them important hits of cosmology. And then once we look at this little bit of history about cosmology and we understand what the goals are, we're going to start by looking at the units that we use in cosmology and also the distance, the most common distance used in cosmology. Then we'll take a look at the cosmological principle. Cosmological principle. Later on, we'll see the Hubble Law. Then we'll take a look at the Scalar Factor. We'll also take a look at the Comoving Distance. We'll take a look at the Hubble Parameter. And to finish the class, then we'll take a look at the Redshift. So let's start by looking at the goals of cosmology, okay? So cosmology as a goal, its main purpose is to study the past, the present, the future, and the content of the universe. So basically, what we want to study is how the universe began, how it evolved to be what we see today, and what is going to happen in the future to this universe. And also we want to know how everything that is inside of our universe has affected each of these timelines, or basically this timeline between past, present, and future. So our goal is then, again, to study the past, present, future, and content of the universe. And so the modern cosmology is actually thought, or people always assume that actually started with Einstein's general relativity theory of general relativity in 1915. And we call it modern cosmology because in reality cosmology has been around for thousands of years, ever since people started looking at the sky and people started to wonder about what was out there. They have been doing cosmology. It's just basically we have a set of different tools that differentiate us from those people. So basically what we say is now that modern cosmology started with Einstein's theory of general relativity. So important hits for cosmology, the first of these important hits is going to be obviously basically in 1915, Einstein's theory of general relativity. Then another hit that came right after Einstein proposed general relativity came around the 1920s, when a physicist named Friedman discovered that there were some solutions to Einstein's equation which allowed for the universe to expand itself. And this was very, very important. Okay, so, and I'll explain in a moment why. So Friedman discovered solution to Einstein's equations, that allowed for a universe to expand. And so this was very important because up until then, everybody thought that the universe was static. Basically, the universe was not expanding, was not moving, has never changed. It was always the same. But this solution to Einstein's equation actually changed this thinking, and basically introduced the idea that the universe can actually expand itself. Later on, this was actually confirmed by Edwin Hubble. So this was done 7 years later. This was done in 1922, but Hubble in 1929 then actually measured that the universe, basically discovered that the universe is actually expanding. So the discovered universe is expanding. Later on, right after that, then we had a physicist named Zwicky. Okay, at least I think that's how you pronounce his name. He found out basically the first evidence for dark matter. And so this is very important because up until that moment, also what it was thought was basically that if you look at a galaxy and then you go from the center of that galaxy outwards radially in that galaxy, then you will expect that as you move out of the center, the velocity of the components of the galaxy will decrease as a function of radius. However, what it was found was basically that the velocity curves, which is what they call away from the center, actually stay constant. And this is basically telling us that there is another component of the universe which we don't understand. And it's basically what we term dark matter. And today is one of the greatest mysteries in physicists and for physicists and cosmologists, since we still don't know what this actually is. There's ideas, there's a lot of hypotheses, but nothing concrete that can be supported so far. So Zwicky found first evidence for dark matter. Then about 30 years later, Penzias and Wilson found the cosmic microwave background, found the CMB. And so this is also very important because it allows us to study cosmology. And the CMB, or the cosmic microwave background, is the first light from the universe that we are able to see. So basically, there's an epoch between the start of the universe and this cosmic microwave background. There's some light that is trapped and basically we cannot see. But then after this moment, this specific moment in time, then light gets free. And that light that gets free is the first light that arrives to us from the universe, and is what we call the cosmic microwave background. So basically, the cosmic microwave background is the first light. The baby is basically a way for us to see the baby universe. So that's why it's very important. It also has also a lot of information about our universe, and it's a great tool that we will also study later on. Okay, same thing with dark matter. We're going to be seeing later on. We're going to see everything so far in just a little bit in some later classes. All right, so later on, okay, in the late 1990s, two teams discovered actually that the universe is not only expanding, but that it's actually expanding in an accelerated way. So basically, we have an accelerated expansion of the universe. This is also something that is revolutionary, is basically something that was not expected at all up until that moment, because until that moment, everyone thought that the universe was simply filled with basically matter and light, and then also until that moment also dark matter. But what we know is that matter attracts itself gravitationally, so means that if we have two objects, they're going to attract each other. And so because gravity is an attractive force, then what it was thought is that even if the universe is expanding and then things are actually moving away, at some point the force of gravity is going to win, and then everything is going to start decelerate. Basically, the matter of the universe is going to start decelerating the expansion, and then everything is going to start contracting. So instead, what we found is that the universe is doing the exact opposite. The universe, what it's doing is actually keep pushing everything apart and making the universe accelerate, or like the expansion to be accelerated. So this is what we actually call dark energy. Although some people, depending on what they're talking about, they might refer this as modified gravity or dark energy. Again, we'll see all of this later on. But again, this is one of the greatest hits as well. And it poses a great puzzle for cosmologists and physicists, since we still don't know why this accelerated expansion is happening. So in the late 1990s, two teams discovered the accelerated expansion of the universe. And then finally, one of the hits that happened in cosmology not so long ago, about 8 years ago, in 2016, is the detection of gravitational waves, of the first gravitational wave. Perfect. All right, so now that we know a little bit more about cosmology, about its history, let's start with the nitty-gritty. We're going to start by looking at the units. In cosmology, what we use is natural units, which I'm going to denote with NU. And what this means, these natural units, the only thing they do is basically, for the speed of light, the reduced Planck constant and the Boltzmann constant is basically it sets up its value to be equals to 1. And the relationship then, to go back, for example, to the international system of units, is, for example, we know is that C is 3 × 10⁸ meters per second. Then h bar, or h, which is this h bar is called the reduced Planck constant. This one is called the Planck constant. The h without the bar is the Planck constant, and this is equal to 1.05 × 10⁻34 joules per second, time second. And then the Boltzmann constant is going to be equals to 1.38 × 10⁻³ 23 joules per Kelvin. So again, this is one of the and so what this actually means, sorry, is that for example, anytime we see something that is kind of like a velocity or something that corresponds to h bar or the Boltzmann constant, then we can set up equal to 1, because we're saying basically that any velocity, any joules times seconds, and any joules over Kelvin, we're going to set up to a unit to be equals to 1. So let's see just what this means in terms of looking at energies, lengths, and anything else. So for example, let's say that we're in quantum mechanics, and in quantum mechanics, we have that the energy is going to be equals to h bar times the frequency of the particle. And so what this means is that in terms of units, then we have that the energy is going to be the units of h bar times frequency. Now we already know that h bar in natural units, we're going to set up to be equals to 1. So this means that the energy in natural units is going to be equals to a frequency. Now, what is a frequency? Frequency is simply a number of cycles divided by a specific amount of time that it takes to do some cycles, or a specific rotation or whatever. So in this case, what this means is that what we have is the energy is going to be equals to 1 over time, right? And this means that is the inverse of time. And now we're going to see how this relates actually to also length. So in just a moment, okay? So let's just go back, let's just stay away from this for a moment. And let's say that we have a length. Length can be related to velocity times time. So in this case, we have length, right? So remember that velocity is equal to some specific length divided by some time, which means that the length is going to be equal to the velocity times time. Now, as we said before, we are setting any velocity to have units of 1. So what this means is that the units of length is going then to be equals to units of time. And so what this means is that if we plug this in here, then the energy in natural units is also going to have units of inverse of length. Okay. Then we can also take a look, for example, at another example, and take a look at the energy density. Energy density is going to be equals to some energy divided by some volume. And so now we know that the energy is going to have units of length inverse, and that the volume, if we are in a three-dimensional space, is going to have units of length to the cube, which means that the units of energy density in natural units is going to be equal to the length, or the inverse of the length, to the fourth power, which is the same as saying the energy density has units of energy to the fourth power in this case. All right, so let us continue by taking a look at units of distances. Now, also, let me just mention before I continue that you'll see that I'm just giving you random facts. I'm just teaching you some basic things of cosmology, okay? But at some point, everything will connect, everything will make sense. So I'm just telling you different things now because we are trying to learn cosmology from the get-go. So we need to learn many different things, and then we'll put back all the pieces together, okay? But in this case, just bear with me, let's do this thing, and you'll see how everything makes sense in later videos, and how we can connect everything. So now we need to measure, we need a measure for distance, okay? Now in cosmology, distances are normally measured in parsecs with the unit that is named a parsec. So what we're going to do, to be able to understand what this is, let us make some drawings where we have the sun, we have the earth here. And the first thing actually to understand the parsec is that we're going to set up, and which is also another unit that is used in astronomy, is the AU, the astronomical unit. Okay, the astronomical unit is defined basically as the distance between the sun and the earth. And this actually is going to help us in order to understand what the parsec is. So let me just pause for a moment. I'll draw another drawing here and then we'll continue. All right, so by taking a look at this drawing, what is a parsec? Okay, basically the definition of a parsec, or that distance of a parsec, is going to be the distance at which an object, an astronomical object, for example, this object right here, sustains an angle of 1 arcsecond from the point of view of the Earth. So what does that mean? So we know that the distance between the sun and the Earth is 1 astronomical unit, okay? And so if we are ever, let's say we're looking right right away out from the Earth along our line of sight, and then we deviate ourselves only by 1 arcsecond, then if we find an object at this location, then by definition the distance between us and that object, which sustains a 1 arcsecond of a degree, then that object is 1 parsec away from us. What does that mean? Well, that basically means that this distance, okay, in terms of other distances, is defined as 1 parsec, is actually equals to 3.2 light years, or what is equal or similar to 3.08 times 10 to the 13 kilometers. So this is the main relationship for the parsec. So let us continue by taking now a look at the cosmological principle. So what the cosmological principle tells us is basically that the universe is homogeneous and isotropic in scales greater than or equal to 100 megaparsecs. So, but what does this mean? What is actually what does homogeneous and isotropic mean? So if we say that the universe is homogeneous, what we're saying is basically that the universe looks the same from anywhere. And if we're saying that the universe is isotropic, we're saying that the universe looks the same in any direction that we look at. Okay, so let us take a look at what this actually means by looking at some examples. Okay, so let's imagine here I have a picture that is extracted from the book from Dragan Horerer, A Course in Cosmology, where we have two great examples of one universe which is going to be homogeneous but is not isotropic. But then we have a universe which is isotropic but is not homogeneous. So let us take a look at figure A here, where we have basically a universe which is composed of blocks. And so what we have is basically this universe is homogeneous because it doesn't matter where I am. It doesn't matter whether I'm here, I'm here, I'm here, or I'm here. The universe is the same because it's made up of bricks anywhere I go. However, the universe in this case is not isotropic because, for example, if I sit at the middle, then I will see that the universe ends up here. For example, it ends up here, but then if I go farther away in this direction, then it ends in a different way. So it's not isotropic. It doesn't look the same everywhere I look, in any direction that I look. But it is homogeneous because wherever I go, the universe is made up of those bricks and it's the same. Now, taking a look at figure B, then if we see it right here in the middle, okay, this is going to be exactly from this perspective only, from sitting in the middle. Then what we have is that the universe is going to be isotropic, because if I look in any direction, if I do a 360, a turn of 360 degrees, 360 degrees, then I will see my universe looks exactly the same in any direction that I go, in any direction that I look. However, if I translate myself from the center to an exterior part, maybe here, or maybe here, or maybe here, then I will see that basically now my universe is not the same. Because, for example, I can be here, I can be living in a line, but then when I go here, then I'm gonna be living in a space. So it is different if I go to different places. And also you can take a look that, for example, it's not the same to be living in the center where everything is like a combination of lines that are intersecting, than living here where everything is now, it looks like I'm living in a space. So the universe from this point of view is going to be isotropic, but in this case it's not going to be homogeneous. All right, so let us take a look now at the Hubble law. Remember that I told you that Friedman basically found out that there was a solution to Einstein's general theory of relativity, saying that the universe was able to expand, that it was possible that the universe could expand. So Hubble in 1920 proposed, or he took the mission to measure this. Okay, so what he ended up finding in 1929 was he basically found a relationship between the velocity of some galaxies and the distance that they are away from us. So let us take a look at what he actually found. So what we see here is in the y-axis, we have the velocity from those galaxies, where actually Hubble got this data, these velocity points, from data that was obtained by Besto Schleifer, or I hope I'm saying his name right, but Besto Schleifer, I think is his name. And then the distance here in the x-axis, this was basically data that he obtained through a method that was actually developed by another physicist named Henrietta Leavitt, where he used cepheidas in order to be able to measure that distance. And just as a reference, cepheidas are actually pulsating stars. These are some stars that pulsate radially towards us. And the period of pulsation is related to their luminosity. All right. So once we found what the actual luminosity of the intrinsic luminosity of a cepheidas should be, then we can compare it against the luminosity that arrives to us on Earth. And then this allows us to find a distance from us to the cepheida. And because the cepheida is always inside of a galaxy, then what we can actually do is that what we are actually doing is actually finding the distance between us and the galaxy that contains those cepheidas, those pulsating stars. So this is basically the way that he did this. What we see is basically the relationship that he found, where again, this plot I'm extracting from the book Course in Cosmology by Dragan Horerer. And from this plot actually is where he found his famous Hubble law, which basically tells us that the velocity of galaxies is related to the distance by the slope of that of this plot, which we're going to call the h naught, and then multiply by the distance between us and those galaxies. And so basically, what this is telling us is that the farther away those galaxies are, the faster they're moving. And what this tells us is basically the universe is actually expanding away from us. Now, just as a reference, the value for H naught today, okay, basically this is today, is going to be equal to 70 kilometers per second per megaparsec. Although, okay, there's actually some tension, basically there's some discrepancies between different experiments. Some early universe experiments are basically telling us that H naught should actually be about 73 kilometers per second per megaparsec, while late time universe experiments are telling us that this should be 68 kilometers per second per megaparsec. And some of you might be wondering, so why is this a problem? Why is this a tension? Why is this like a discrepancy between them? And the reason for this is actually that the experiments are getting better and better. So what this means is the errors that they have every time is smaller and smaller. And so what we see is basically that even though they have smaller and smaller errors, they are actually getting farther away, which is a problem because the early universe is telling us something and the late time universe is telling something else, which could also imply that we don't have the complete physics right. But again, this is something to be explored in the research field. And for now, I'm just commenting it so that you can know about it too. All right, so let us continue by studying now the scalar factor. So the scalar factor is going to be a mathematical way for us to actually capture the fact that the universe is expanding, okay? So as we said before, we thought that the universe was static. However, we know this is not the case. It's actually expanding, so we need a way to capture this mathematically. So how can we do this? Let's start by first drawing. We're going to draw a two-dimensional space which is going to represent our universe. And so what we see here, let's say for example that in this two-dimensional universe, this is also a static universe. This universe is not going to expand. So if we have 2 points, let's say one point here, another point here, then the separation between these 2 points, we can call it ds. And then this is going to be given by the Pythagoras theorem by the differentiation in the x coordinate and the y coordinate. So what this means is that we can write our universe in terms of ds squared equals to dx squared plus dy squared. This piece of information about the universe is basically telling us how the geometry of our universe is telling us information about the change or like the difference between points in our universe. And this is what we call the metric in cosmology, okay? Now, in this case, because there's no change as a function of time, then our universe or this metric is not going to capture any change in time. It's just a static universe. But what happens when we have a dynamic universe? In this case, then we might start with a universe that looks exactly like this one. So let us copy it here and let us paste it. And then after some time, then we might actually get an expansion. Basically, our universe is going to expand. So as a function of time, then we increase our universe. Or we could also even have the exact opposite, that as a function of time, then our universe was going to contract. Okay. Then what actually happens here is that we need something that captures this change as a function of time. What we're going to say is basically that this ds is going to stay the same, but what is going to actually change is going to be our differential part in the X and the Y, and same thing here. And we're going to capture that change with this new parameter A of t, which is what we're going to call the scalar factor. Okay, so let me just write it here, and then we're going to write how our metric is going to look right now. So basically now we can write our metric, the piece of information, or basically the mathematical equation that gives us information about our universe, about its geometry, is going to be given then by A of t squared times dx squared plus dy squared. So as you can see, it's basically the same metric as we had in a static universe, except now our metric or this scalar factor, which depends on time, is going to make that our universe either expands or contracts. And how do we know whether it contracts or expands? Well, if we take the change in the scalar factor, let's say the derivative, right, which is equal to the change in our scalar factor over change in time, and we see that this is positive, then this implies that the universe is expanding. But if we find that the derivative with respect to time, or the change in a scalar factor or change in time, is negative, then what this means is that our universe is actually contracting. And this basically gives us a little bit more of information about our universe. All right, so now we continue with the comoving distance. And comoving distance. And to understand what this is, let us once again draw a coordinate system where basically it's going to represent our universe, okay, which is going to start with some specific time, and then it's going to evolve to, after some time, to basically maybe expand or contract, whatever we want, okay? And so let us say basically that we're going to define the distance between squares in, so basically this distance between squares here. Each space is going to be defined as basically 1 unit. 1 unit of whatever we want. And likewise, same thing here. This is going to be 1 unit, okay? Because this is our coordinate system. And is going to expand alongside the universe. So basically what we're saying, okay, is that the comoving distance, or let me just start over. What we're going to say basically is that our universe has a coordinate system which is going to expand alongside the universe. And what this means for us is that the distance between spaces, like the distance that we see, is going to increase, okay? But the distance in our coordinate system is actually always going to stay the same, okay? So if we had one galaxy here and then we had one galaxy here, in after some time t, then within our coordinate system, the galaxies will still be at this point and then at this point. And the distance between them will always be the same in our coordinate system. This coordinate system is what corresponds to our comoving distance. So basically, this comoving distance is a distance that does not change as a function of time. It's basically something given by a coordinate system in the universe. And there's a way for us to actually explain or relate this comoving distance with the physical distance that we actually see. So what we're going to say is basically that the physical distance that we see, okay, the one that we actually measure, the one that we actually see that changes, is going to be given by the scale factor, which is going to encapsulate that information about how it changes, times the comoving distance that we're going to say it does not change. It's basically the comoving distance is going to be basically the distance given by a reference system that is expanding alongside the universe, but that we want to relate to our physical distance by having this scale factor. So that's why, for example, the scale factor is also going to be important in our analysis of cosmology. All right. All right. So now that we understand what the comoving distance is, or at least I hope that you understood what the comoving distance is. If it's a little bit unclear, please let me know. I will try to put another explanation which makes more sense. Hopefully something that is more clear to anyone that got lost. So let us now take a look at the Hubble parameter. Let us study what this is. And so to be able to understand what this is, we are going to be starting from this equation that we have for the comoving between the relationship between the physical distance and the comoving distance. So what we're going to do is we're actually going to take the change in time for this equation, okay? And so what this looks like is, for those that know calculus, is taking the derivative of both sides, or what is the same as basically the change in of all the parameters there over the change in time, okay? So this is going to look like this, where we take on the right-hand side, we are taking the change in the physical distance over the change in time. And then on the right-hand side, we're going to take the change in the scalar factor as a function of time over the change in time, times the comoving distance. And we don't take the change in the comoving distance, okay, because what we actually have is that the change in the comoving distance as a function of time is going to be equals to 0, since we know that the comoving distance does not change as a function of time, okay? That's basically the definition of the comoving distance, is a distance that is integrated, is intrinsic of a coordinate system that moves along with the expansion of the universe, and that the distance between any 2 points in that specific coordinate system never changes, okay? So again, it's like saying that we have a galaxy here and a galaxy here, and then it doesn't matter as we move forward in time, whether the universe expands or contracts, the distance is always going to be the same. So that's why this part is going to be 0. So now, again, going back to the Hubble parameter, then we have to realize that the left-hand side of this equation is actually a velocity. It's the velocity, it's a physical velocity, okay? So it could be the velocity of stars, the velocity of the galaxies that we see. Then on the right-hand side, then we have, again, the change in time of the scalar factor. And what we're going to do in order to make this equation actually make sense is we're going to divide by the scalar factor, and then we are also going to multiply it by the scalar factor. So basically we're doing a multiplication by 1. And then we have this resulting equation. But now take a close look at these two terms, the A times the comoving distance. This is our original definition for the physical distance, which means that what we have here is going to be the change in distance, the change in scalar factor over the change in time, which we're going to denote with this A dot divided by the scalar factor times the physical distance, okay? And if you realize, this is actually the same as the Hubble law, but as a function of time, since our scalar factor can change in time. So basically we were able to reproduce a generalized version of the Hubble law that depends on time. So what we have is velocity as a function of time equals to this a dot over a times some distance. And if you realize we plugged forward, well, before we do that, then now what we can define as the Hubble parameter, okay, is actually going to be this scale, this a dot over a. This is what we define as the Hubble parameter. And this is also one of the many things that we can measure in cosmology that gives us a lot of information. So then this is going to be equals to h of t times that physical distance, okay? Now realize what happens when we have time is equal to the time today, okay? That t naught. What happens is that we have a velocity evaluated today equals to the Hubble parameter evaluated today times some distance. And what does this mean is that basically that this h naught or this h evaluated at the time today must be equal to h naught in order to reproduce the Hubble law, the relationship that Hubble found in 1929. Okay. So this is what the actual Hubble parameter is. It's going to be this change in how the velocity of galaxies, or basically the expansion, changes as a function of time. It's basically, it encodes that information. All right, so with this now we arrive to the last section that we're going to be taking a look at today in this class, which is going to be redshift. And so what is redshift? So redshift is actually a phenomenon that occurs due to the accelerated expansion of the universe, due to that expansion of the universe. And so what happens is basically, let us imagine that we have an object at some point A, okay? And this object is going to emit some light, okay? And light, as we know, is also going to be a wave. And because it's a wave, then this wave has a specific wavelength, okay? Where the wavelength is given between the peaks of this wave. And this is what we're going to denote with this Greek symbol, lambda, and then with the subscripts EM, lambda emitted. And let's say that this light arrives to us at some later time. What is going to happen is that because the universe is expanding, then the universe is also going to expand, is going to stretch that wavelength. And then we're going to find a greater wavelength is arriving to us. So what we're going to measure here on Earth is a wavelength that is or observed wavelength that is going to be greater than the emitted wavelength. And so what we define basically as redshift mathematically is going to be as the difference between both the observed and the emitted wavelength divided by the emitted wavelength. And this is an important relationship because it encodes a lot of information about the expansion of the universe. It can also be related to the scale factor, as we will see later on, and also to time itself. So it's going to be, it basically is a key piece in order to do cosmological analysis in today's modern cosmology. So with this, we've arrived at the end of this class. I hope you liked it. Hope you had a great time and you learned a lot. Please let me know your comments and see you next time.